Hello and welcome to EngPhys 3004 lecture numbers 20 and 21. We're going to be looking at internal flow convection now. So recall internal flow through a pipe. We have a situation where flow develops through what's called the entrance region. This is where the velocity profile is changing in the length direction, which we're going to call x. Once you're fully developed, then the velocity profile, which is how it looks across a cross-section, doesn't change with length anymore. With that analogy in mind, we're also going to define the thermal entrance region. So when you start flow entering a pipe, you've got these boundary layers that form at the edges as the fluid inside maybe is like heating up from contact with the hot walls of the pipe there, yeah? So as the temperature of the fluid next to the walls increases, and then increases the temperature of the fluid next to that, next to that, next to that, then we've got this boundary layer that develops. So because the fluid is flowing, the temperature at the center, right at the entrance, is not going to be changing in as the flow keeps moving, right? That's still going to be close to the temperature of the entering fluid, but the wall temperature is going to be affecting the fluid right beside the wall. Now, as you move along, eventually the wall temperature has affected the inside of the fluid, and the boundary layers from temperature, so the thermal boundary layers, have gone and intersected with each other. They've gone and matched at the center. And after that point, we call it thermally fully developed. Now, past that point, you don't have the situation where the temperature of the fluid is constant anymore. So while past the velocity fully developed region, so past the entrance region, that is, in the fully developed region for velocity, the velocity profile doesn't change with distance. The average velocity is a constant all the way along. Meanwhile, for temperature change, the temperature of the fluid is changing all the way along, even past the end of the entrance region. So in the fully developed region, if the walls are a different temperature than the fluid, then they're going to be still affecting the temperature of the fluid as it moves along. So what's going on is in the fully developed region, you've got the relative temperature profile being a function only of position, not of position along the length of the pipe anymore. So it doesn't change as you move further along the pipe. Now, the other thing that this means is that the convection coefficient is a constant in the fully developed region. So in the entrance region, you've got extra heat flow because of the thin boundary layer, but then once you're fully developed, there's less heat flow because the boundary layer is going to be thicker. And the convection coefficient that we're defining in the fully developed region is going to take into account the temperature profile that we're talking about. So when we say it's fully developed, we're saying that the relative temperature at any point compared to the surface, relative to the mean temperature compared to the surface temperature, is not changing anymore in the length direction. And that means that the shape of the profile is the same, so the convection coefficient will be a constant as we are in the fully developed region. Okay, now in terms of entrance lengths, the thermal boundary layers can either coincide and have a fully developed thermal region before or after the fluid boundary layers have coincided. So if you have a situation where you have a low Prandtl number, this would be like a liquid metal, something with a really high thermal conductivity, then the thermal boundary layers will develop faster, whereas for a high Prandtl number, they'll develop slower. If they develop slower, then you have a larger thermal entrance length than you do in laminar. Recall, than you do for the velocity, the hydrodynamic entrance length. So the velocity entrance length for laminar flow was 0.05 Reynolds number times the diameter. It turns out that for turbulent flow, the extra mixing from turbulence means both entrance lengths are basically the same and set at the hydrodynamic one, which is 10 diameters. Recall the hydraulic diameter here that we use. So hydraulic meaning referring to the part that gets wet on the inside of the surface. So the wetted perimeter diameter to use is 4 times the cross-sectional area divided by the wetted perimeter. And that's the D that we're using in these formulas. So this works out to just the regular diameter if you have a circular cross-section, but then also accounts for other non-circular types of pipes too. Now, the Reynolds number that uses this diameter, recall that the Reynolds number was the average velocity times diameter divided by kinematic viscosity, or density times average velocity times diameter divided by the dynamic viscosity mu. Now, Reynolds number for an external flow situation around a sphere, we said turbulence onset was around 200,000, maybe 2 million to say for sure that it's turbulent. For internal flow, recall that the transition, the critical Reynolds numbers were a lot lower. So 2300 under that is where you can say it's laminar, and definitely turbulent above 10,000. Transitional in between, kind of depending on the roughness, whether you have turbulence. Okay, so the task to determine the Nusselt number is what we're going to end the chapter with. But before we do that, we're going to be looking at some interpretations of heat flow inside internal flow in the first place. So things are going to be a little bit different in internal flow. For instance, we don't have necessarily like a surface versus a free stream that we could use before. So like what is the free stream when you're talking about internal flow? What we have instead is the mean temperature. Use mean temperature rather than like the center temperature, because the mean temperature across the cross section is going to be better for determining energy calculations, which we're going to do in the next section. Okay, now let's look at a section of fluid in a pipe, flowing in a pipe. It's got this mass flow rate and some specific heat capacity there, and it's got some inlet average temperature across this surface, and then some different temperature at the exit. If we're ignoring any kind of internal friction generating heat in the inside, then it must be because heat has flown into it. So there must be heat added if the temperature is higher at the exit than it is at the entrance. And you could say from an energy balance that specifically the rate of heat added is the mass flow rate multiplied by the specific heat capacity times that temperature difference, average at the exit minus average at the inlet. And the reason that we use averages in the first place rather than say the mean temperature when we're defining convection stuff earlier is so that this energy balance is going to work out nicely. So we're going to look at two different situations. First situation is constant surface heat flux. So the heat entering per unit area, the rate of heat entering per unit area over here in the pipe would be the same over here, over here, over here, all the way along the length of the pipe and all the way around each section of the pipe. In that situation, you can say that the total rate of heat flux is just the rate of heat flux per unit area, so the rate of heat flux density, multiplied by the total surface area. And from the energy balance, that would be the mass flow rate times specific heat capacity times the temperature difference. Okay, and why even stop this? There was nothing really special about the exit temperature. If you use a different surface area that's earlier along, you would have that the heat added would be reduced linearly. And so since the mass flow rate and the specific heat capacity are the same, the exit temperature must be reduced linearly. It must linearly approach the inlet temperature with that same slope. So all of this says that in a situation of constant surface heat flux, you end up with a mean surface temperature, which is linear as you increase the length of that pipe. So the surface temperature flux lets you solve for the surface temperature if you know what the convection coefficient is. So at any point, the surface temperature flux, the surface heat flux density, I guess we should call that surface heat flux, and really it's the surface heat flux density. Yeah, so this would tell you what the temperature of the surface has to be for this energy balance to work. So the rate of heat entering at a given spot must be equal to the convection coefficient times the difference between the surface and the mean temperature. And so the surface temperature has to be equal to this mean temperature plus Q dot divided by H. Now, since the mean temperature we figured out is linear, this lets you figure out what the surface temperature has to be doing. In the fully developed region, H is a constant. So this difference from the mean temperature must also be a constant, which means that the surface temperature is a constant offset from the mean temperature. In the entrance region, though, H is different. Specifically, it's higher. So if H goes up, then the difference between the surface temperature and the mean temperature is not as much. It gets lower. In fact, going back to the picture of the boundary layers, that kind of makes sense too. If you've got this constant surface heat flux situation near the entrance region, the surface temperature is going to be similar, closer to the mean temperature. The mean temperature is much closer together to the situation at the surface. Now, if you have constant surface heat flux, that's sort of a strange situation. If this was a constant surface temperature, then you'd expect the heat flux to be higher at the entrance than it is later on. And in fact, that's what we're going to deal with next. So the second situation, constant surface temperature. Now in that situation, you have a higher difference at the start, right? And that's where most of the heat is going to be flowing, but that's going to cause the temperature to change. And as the heat flows in from, let's say, imagine, so I guess we should say that if this is the surface temperature up here, then the fluid is colder and the heat is flowing from the surface into the fluid, and that heats it up. And then there's less of a motive for temperature, for heat to flow, because the temperature difference is lower. So then the little bit further along, even if the convection coefficient is the same, you have a lower heat flux from that, lower heat flux all the way along for the constant surface temperature situation. So the temperature inside the fluid, the mean temperature, should exponentially approach the surface temperature. And in fact, it does. The temperature at the exit is the surface temperature minus the difference between surface and inlet mean temperature times this exponential function here. First, let's see why this kind of makes sense. So the exponential function exponent is convection coefficient, total surface area of the fluid in contact with the surface. The mass flow rate and specific heat capacity are in the denominator. So other things equal, if you increase the mass flow rate, then you are going to make the exit temperature closer to the inlet temperature. The surface temperatures are going to cancel out, and this is more fully because this exponent is going to be smaller, so we're going to be close to 1. So the exit temperature gets closer to the inlet temperature if you increase the mass flow rate or increase the specific heat capacity, because it takes more heat to change that fluid temperature in those situations. On the other hand, if you have more surface area or more convection coefficient, then you are going to move the exit temperature closer to the surface temperature, further away from the inlet temperature. If you rearrange this equation and solve for an appropriate exponent that we're going to see later, then we'll find out that the effective temperature difference to use for defining convection for this situation is what's called the log mean temperature difference. Log mean temperature difference is a bit of a complicated ratio. It's the difference in the temperature difference at the end and the temperature difference at the start, expressed here. Temperature difference from the surface, that is, divided by the log of their ratio. Log mean temperature difference. Now, where does this, first of all, why does log mean temperature difference show up from this formula here? Well, if you take the second equation here, this equation for the exit temperature being exponentially changing towards the surface temperature from the inlet temperature, if you were to rearrange this and solve it for m dot Cp, then you'll find out that m dot Cp multiplied by Te minus Ti has to be equal to this, where log mean temperature difference is defined here. And since m dot Cp times Te minus Ti is the heat flux rate, then that has to be equal to then this temperature difference is exactly the one that you need to use for defining convection. So where does this formula come from then? Where does this exponential decay specifically come from? Can we derive it? And the answer is yes. So let's do that. We've got a small element of fluid, and we've got a little bit of heat going into it, and that's equal to H times the surface minus the mean temperature by our definition of how H works now. It's not the free stream, and it's the mean fluid temperature, multiplied by the little bit of area that is in contact wall to the fluid. So that would be perimeter multiplied by dx. That would be dAs. That's this right here. And then the amount of heat that's flowing in would be the change. So the heat flow rate there would be the rate of change of energy of this section, which would be its mass flow rate specific heat capacity times the change in temperature as it crosses this little dx distance there. So that's this. And now this change in the mean temperature would be the same as negative the change in the surface minus the mean temperature, because the surface temperature isn't changing, so you can add that in, no problem. And now we've got a first order separable differential equation in Ts minus Tm as a function of x. If you rearrange and then integrate, and then substitute in the initial condition that Tm at x equals 0 is Ti, you can solve for what Tm is as a function of x. If you put in that Tm at x equals L is Te, the exit temperature, then you've got exactly the relationship above. So again, solving this thing for m dot Cp will give you a negative HAS divided by this logarithm. So multiplying both sides by Te minus Ti tells you exactly the log mean temperature difference to use in this heat flux equation. All right, then, to summarize, for a constant surface temperature, the temperature difference exponentially, the temperature of the mean temperature in the fluid, that is, exponentially approaches the surface temperature. And the exponent here, this HAS divided by m dot Cp, has a name. This is called actually the number of transfer units, and it's going to be pretty important when we're in chapter 22 and dealing with heat exchangers. So for a constant H, which is again the case for a fully developed flow, you can double the number of transfer units by doubling the length. So this is only then a function of the length that we've got, so the length of the pipe section we're looking at. But this doesn't quite halve the temperature difference, right? If you have, because of the exponential decay, you're going to get really diminishing returns as you make the pipe longer and longer. We'll focus on heat exchangers more in 22, as we said, but now the simple answer is that a heat exchanger generally targets NTU is 1 to 1.5, because if you go past that, it usually isn't worth the material cost to the pipe and the extra pumping power from pumping through a longer pipe. Let's recap. We've looked at separate situations when you have constant surface heat flux and constant surface temperature. We said that for constant surface heat flux, we end up with, from the energy balance, the Q dot total energy flow rate in, total heat flow in, is the mass flow rate times Cp multiplied by the temperature difference. That's true whether you've got constant surface heat flux or constant surface temperature. This is definitely true. So all the energy that goes in heat has meant a temperature change in the fluid going out compared to the fluid going in. And the rate of heat entering is m dot Cp Te minus Ti. Okay, now if you have constant surface heat flux, you can also say that this energy balance must be equal to just Q dot As, and that's pretty easy to figure out if you know that constant surface heat flux. You just multiply by the surface area, and that lets you solve for what the temperature is at any given length. So you can figure out the exit temperature from knowing the inlet temperature and the rate of heat flux, so the heat flux density. Then if you want to know what the surface temperature is for that, you're going to need the convection coefficient. On the other hand, if you know that the surface temperature is constant, then to figure out what the exit temperature is, you need to know the convection coefficient, and after rearranging, you need to know the convection coefficient just to find out what the total rate of heat flux is as well. So either you kind of start with the rate of heat flux and can figure out the temperature change quite easily in the constant surface heat flux situation, or for the constant temperature situation, you know the surface temperature and you have to do a little bit of work through convection coefficient to find the rate of heat flux and the exit temperature in terms of the inlet one. Now, the last bit of information to deal with all of these situations is where we get the convection coefficient. So for that, we're going to look at calculating some Nusselt numbers. First up, laminar flow. Laminar flow, Nusselt numbers are going to depend on whether we have uniform surface heat flux or uniform surface temperature. The Nusselt numbers are not the same in laminar flow for those two situations. Laminar flow, fully developed, we have a well-defined parabolic velocity profile, so you could actually do the math in order to calculate the amount that the convection coefficient has to be by the same kind of thing that we did in the earlier part of chapter 19, where we looked at these velocity where you look at sort of an energy balance and a temperature gradient at the wall in order to figure out what the convection coefficient has to be. And if you do all of that, then you're going to find that the Nusselt number for uniform surface heat flux fully developed laminar flow is exactly 4.5 4.36. Well, I mean 48 over 11, so I guess I should say 4.36 with some extra decimals there. And if you've got uniform surface temperature, then it's 3.66. So it's higher by a little bit for uniform surface heat flux than it is for uniform surface temperature. If you have a non-circular tube, then you can check out table 19.3 to see a number of different surface temperature and surface heat flux Nusselt number situations. And for developing flow, there's a little bit more complicated formulas to use. So if what you would do is you check the entrance length formula from earlier. So back up in 19.5, we had that the hydrodynamic entrance length in laminar flow was 0.05 Reynolds number times diameter, and then the thermal entrance length is the Prandtl number times the hydrodynamic one. So if you have a large thermal entrance length compared to the length of the tube, maybe longer than the tube or at least an appreciable amount of the tube, then it's better to not use this first formula, which is really only valid for fully developed flow, but to use some of these formulas depending on what other parameters you have. So these are both for uniform surface temperature. So that's why it's 3.66 plus this correction factor, similar to the 3.66 earlier. And you would have a bit of a higher Nusselt number then if the flow is still developing, and that's appreciable. So this is if viscosity is assumed constant. That would be the case if viscosity doesn't change too much with the temperature for the temperatures involved. But if viscosity is not a constant, then it's better for you to use this second formula here, where mu b is evaluated at the bulk mean fluid temperature. So mu s is evaluated at the surface. All the other ones are at this different parameter here. Again, bulk mean fluid temperature, which is, by the way, the average of the average temperature at the inlet and the average temperature at the exit. So the average at the inlet is again the mean one, the one across the cross section, same as at the exit. If you average those two averages, then you get the bulk mean fluid temperature. And that's the one you use to evaluate properties, except for mu s, which is the surface temperature viscosity for the fluid. You have other geometries too. So here's a situation for isothermal parallel plates. For turbulent flow, things are going to be a little bit more complicated in that it's often going to depend on the friction factor. So recall in chapter 14, we learned that you can iterate using the Colebrook equation to find out what the friction factor is in a pipe, depending on the surface roughness. Or if you want to just get an approximate first guess, then you can use the Haaland equation. And for a smooth pipe, this transforms into the Prandtl equation. So that's this. This is basically the Haaland equation after you've substituted in epsilon is a 0. Okay, so using these, you can come up with some calculations for Nusselt number. So the book starts off with the friction factor for fully developed turbulent flow with smooth surfaces approximately given by the first Petrikov equation. And this is another friction factor approximation that's valid for a certain range. And then the Nusselt number, if you were to go and calculate this, can be figured out from the Chilton-Colburn analogy using this friction factor. Now, if you go to substitute in this friction factor calculation in terms of Reynolds number into this Nusselt number calculation, then you end up with the Colburn equation. And this works okay, but you can improve it if you let the exponent be different depending on whether the fluid is being heated or cooled. So rather than just a third, you use 0.4 for heating and 0.3 if the fluid is cooling from the surface of the pipe. Now this one has another name. This is the Diedis-Bolter equation, and it gives better results than the Colburn equation. All of these, again, use the bulk mean fluid temperature like we had in the laminar situation. If the variation in fluid temperatures is pretty different, then again, there's a correction similar to what we were dealing with before, where you look at the surface temperature versus the bulk mean fluid temperature, and the other ones are still at the bulk mean fluid temperature. And this is a calculation by Sider and Tate. Now, all of these give errors up to 25%, which is pretty huge. So to improve things, we probably need to use a more complicated second Petrikov equation, which is shown here, including the -1000 factor to improve its accuracy at low turbulent Reynolds numbers, which then turns it into the one that we're going to use most of the time, which is the Nusselt equation. So in the Nusselt equation here, you can use the friction. You still need to use another equation to calculate the friction factor, and for that you probably ought to use the Prandtl equation, which again is the Haaland equation after you've substituted in that epsilon is 0. All of this is really for smooth pipe flows, smooth-walled pipes for the most part. And we'll see some complications with roughness soon. So first off, these also only work down to a certain amount of Prandtl number. At extremely low Prandtl numbers, like you can have in liquid metal flow, then there's some additional special formulas here. So this is a situation where the thermal boundary layer can actually outpace the mixing from turbulence, and you can have different kinds of heat transfer going on. So in that situation, you end up with Nusselt numbers which are calculated using these two equations instead. And in that case, because again the thermal boundary layer is outpacing the mixing from turbulence, you end up with a situation where even though it's turbulent flow, we do have a difference between uniform surface temperature and uniform surface heat flux. All right, so one last note is, what about roughness? So roughness at the walls actually increases the convection coefficient a fair bit, so it can increase H by a factor of 2 or more. To handle it, the best that you can do is use the F, so the friction factor, calculated for rough surfaces from, say, the Colebrook equation or a Moody chart, and then use equations like the Nusselt equation. But it turns out this isn't really as good as using a special Nusselt number equation for extremely rough pipes, in that if you do have an extremely rough pipe, since this equation will cap out at about the friction factor going to 4 times the smooth one, when in reality the H should keep increasing. Now, entrance lengths. Turbulent entrance lengths are typically very short, so basically just ignore them and use these above relations for the entire tube, recognizing that it's probably going to be an underestimate of the actual convection coefficient if the entrance length is important. And for non-circular tubes, what you can do is, in the core region, the velocity is nearly uniform, at least after you time average it. So the velocity change mostly happens in this viscous sublayer. So in a non-circular tube, just use the same relations as we just had, except replace the diameter with the hydraulic diameter. The final thing we're going to talk about is flow through a tube annulus. So this is if you have two concentric cylinders and you're looking at the flow between them. So in the annular region here, not through the center cylinder, but through the region between the two cylinders. In that case, the hydraulic diameter, it turns out to be the difference in the outer cylinder's diameter and the inner cylinder's diameter. Well, I guess the outer cylinder's inner diameter and the inner cylinder's outer diameter, yeah? So the difference in diameters as seen by the fluid flowing through there. Now there's a separate Nusselt number and convection coefficient in laminar flow for the outer and inner surfaces of the annulus, but both use the same hydraulic diameter. So use the hydraulic diameter of this annular region. Typically, this setup would show up in a heat exchanger where the annular flow exchanges heat with the interior flow. So this is something that we're going to see pretty soon in the next section, flow around this interior pipe part. So this is one pipe that has fluid flowing through it, and then you've got fluid flowing around that to try and exchange heat. And in that situation, this outer surface would be adiabatic. So we're going to be looking at a situation where heat can't flow through the outer surface, so there's only heat exchange happening on the inner surface, and then you have just this inner surface Nusselt number calculated here depending on the ratio of the diameters. So still laminar, which means it's a constant, but it depends on what the ratio of the diameters is, which one you should use. The table also lets you deal with the other situation where there's no heat flow happening on the inner surface. So the inner surface is adiabatic and you're flowing just out from the outer surface. And then, depending on the ratio of the inner to outer diameter, the Nusselt number you should use is in this part of the table. For turbulent flow, the inner and outer convection coefficients are approximately equal. Doesn't matter which surface you're transferring heat at. And you can treat the annulus like a duct with this hydraulic diameter. The hydraulic diameter is the difference to get the Nusselt number from any appropriate one of the earlier equations, like the Nusselt equation. And then correct nu by multiplying by a correction factor if one of the walls was adiabatic. So depending on which wall it was, If it was the outer wall that was adiabatic, multiply by this correction factor. And if it was the inner wall, multiply by this correction factor. At least that's what the textbook says. Now, it's a little bit strange that these two correction factors are exactly the same. So just to check, I went and looked up this Pechikov and Roizen paper that these equations came from, and here it is here. So I'm not quite sure exactly what this is talking about, but I think it says that there's maybe like a 5% something if you use these different correction formulas. And anyway, it looks like the second correction formula is actually supposed to be different from the first one, and the book is dropping the factor of this this zeta term there, which looks like it should be 1 plus 7.5 d2 over d1 minus 5 over the Reynolds number. So anyway, if you're in an industrial setting before you go and use these two formulas, I think you might want to just go and double check things with the actual source literature, maybe get somebody that speaks Russian to help you out with what this paper is talking about, or look at one of the future papers that have gone and cited this and summarized it a little differently.